This video is the beginning of Chapter 1, and this is Section 1.1, Making Sense of Data. First, we need to know what is data analysis. Data analysis is the organizing, displaying, summarizing, and questioning of data in order to understand what the data is saying. Some definitions that you need to know are individuals. Individuals are the objects described by a set of data, and so individuals may be people, animals, or things depending on what your data is talking about. Basically, individuals are the objects that your study is actually describing. Variables are any characteristic of an individual. A variable can take on different values for different individuals. So some examples of variables might be your height or your weight or your hair color or your GPA or your zip code. Consider a database that you are part of and then ask yourself, who are the individuals being described and what are the variables? So one database that you are all part of is the 720 students that go to East Rutherford High School. The individuals that we would describe anytime that we were considering the database of those students would be any student that was enrolled. And variables that we might look at is we might look at your GPA. We might look at what grade you are. So are you freshman, sophomore, junior, senior? We might look at your zip code. We might look at your socioeconomic status, the number of absences that you've had in the year. Basically, your variables can be placed into two categories. You have categorical variables, which place an individual into one of several groups or categories. This would be like, do you have blonde hair? Are you a redhead? Do you have a job after school? Quantitative variables would be numerical values for which it makes sense to find an average. This would be like your GPA, your number of AP classes. It is important, though, that you note that not all numerical data is quantitative. For example, I mentioned when we were talking about variables for our database of students at East Rutherford High School, the zip code. Zip code is one of those things that would not be considered a quantitative variable, but would instead be considered a categorical variable. Whenever we are talking about quantitative variables, it's very important that we know that we can find the average of those numbers. However, it makes no sense to find the average of a list of people's zip code. For this first example, we are going to consider the following 10 students from Canada and the information about them, and then answer the questions below. So as you can tell from the table, we have several different columns, and each one of those columns gives us information about a student that's from Canada. If you notice, there are 10 of those rows in our table. And some of the columns that you see province, you see gender, languages spoken, handed, so left-handed, right-handed, or are they ambidextrous? The height in centimeters, wrist circumference in millimeters, preferred communication, travel to school in minutes. So the individuals in this data set would be anyone that we talked to and collected data from. And so in this case, we know that our individuals would be the 10 students from Canada. And so the next question is, what variables were measured? Identify each as categorical or quantitative, and in what units were the quantitative variables measured? So if we look at our table, each column in our table is a variable that was measured. And so if we go through these, we can identify them each as categorical or quantitative, because we know that categorical is kind of like a group that we can put this person in, and quantitative would be a number value that we could find the average of. And so province would be an example of a categorical variable, because we could group all of these people based on where they live. Gender would be a categorical. Languages spoken, however, would be quantitative because I could find the average for the number of languages spoken from these 10 students from Canada. Handed would be categorical because it can't exactly find the average handedness of a group. Height would be quantitative because I could find the average height of this group. Wrist circumference would also be quantitative. Preferred communication would be categorical. And travel time to school would be quantitative. It says in what units were the quantitative variables measured, and that's kind of obvious. This particular variable is languages spoken, so if I were to find the average for the languages spoken, the units would be languages spoken. The height would be in centimeters, it tells us that. Wrist circumference would be in millimeters, and travel to school would be in minutes. So the last question for this example asks us to describe the individual in the highlighted row. So when we are describing the individual in the highlighted row, we literally just say everything that we can tell about this person just from the data that we've collected. So from this data, we can tell that this is a male student from Ontario who speaks 3 languages, is left-handed, has a height of 120 centimeters, a wrist circumference of 100, likes to internet chat, and travels 10 minutes to school. The next important definition is distribution. Distribution tells us what values the variable takes and how often it takes these variables. So we have a couple of different ways that we can explore data. The first is to begin by examining each variable by itself and then move to study relationships among the variables. The second is to start with graphs or a graph and then add numerical summaries. So in your Check Your Understanding section, Jake is a car buff. He wants to find out more about the vehicles that students in his school drive. He gets permission to go to the student parking lot and record some data. Later, he does some research about each model of the car on the internet. Finally, Jake makes a spreadsheet that includes the car's model, year, color, number of cylinders, gas mileage, weight, and whether it has a navigation system. Who are the individuals in Jake's study? The individuals in Jake's study are the cars in the parking lot. Question 2 says, what variables did Jake measure? Identify each as categorical or quantitative. The variables that Jake measured were the model, which is categorical, the year, which is quantitative, the color, which would be categorical, the number of cylinders, which would be quantitative, gas mileage, which would be quantitative, weight, which would also be quantitative, and then navigation, which would be categorical. Next, we're going to move on to analyzing categorical data. The first example that we have is an example of distribution of a categorical variable. And so it has to do with radio station formats. So it says the radio audience rating service, Arbitron, places the country's 13,838 radio stations into categories that describe the kinds of programs they broadcast. Here are two different tables showing the distribution of station formats. So on the left, you'll see a frequency table. A frequency table just means this is how many of each category that we have. You can see at the bottom we have a total of 13,838, which is what they told us up here in our problem. And so if we were to go through and count up all of these stations, it would give us a total of 13,838. A relative frequency table, though, looks a little bit different because this gives us the percent of the stations. And so basically what happens is, to get the adult contemporary, we see that we have 1,556 in the frequency table. In the relative frequency table, it shows us that accounts for 11.2% of the stations. And so the way that we find that is we take 1,556 and divide it by 13,838. So 1,556 over 13,838 gives us approximately 0.112. And if we were to change that into a percent, because our relative frequency table is always done on a percent, we would bump our decimal back 2 places to get 11.2%. So, some definitions that you need to know is frequency table. Frequency table is a table which displays the counts for each category. And a relative frequency table is a table which displays the percents for each category from the total. So now we're going to kind of look at some types of graphs. So one type that we'll talk about is a pie chart. And so with a pie chart, I'm sure you're familiar with this, but it is a circle that looks like a pie, and each one of the shapes inside is a triangle that represents how much it makes up of the total. So, for example, the slice that they've pulled out is the country slice. This slice occupies 14.9% of the pie because 14.9% of radio stations have a country format. So if we look back at our original table that we were talking about, country was at 14.9, so it does make up 14.9% of our pie chart. The next that we talk about is a bar graph. And so you can see it on the bar graph, country was 14.9%, and so it is close to the top and around 14.9 on our bar graph. So a pie chart, the definition for that is that it shows the distribution of a categorical variable as a pie whose slices are sized by the counts or percents of the categories. A pie chart must include all the categories that make up a whole. Use a pie chart only when you want to emphasize categories' relationship to the whole. A bar chart is a bar graph that represents each category as a bar. The bar heights show the category counts or percents. Bar graphs are more flexible than pie charts. A bar graph can also compare any set of quantities that are measured in the same units. So the next example has to do with choosing the best graph to display the data. And so your problem that you have is having to do with portable MP3 music players such as Apple iPods and how popular they are, but they're not equally popular with people of all ages. And so what you have in your table are the percents of people in various age groups who own a portable MP3 player according to the Arbitron survey of 1,112 randomly selected people. And so you can tell in your chart that you have age groups in years, and you have those grouped 12 to 17, 18 to 24, 25 to 34, 35 to 54, and then 55 and older. You also have the corresponding percent of people owning an MP3 player within those age groups. And so you can see by just kind of glancing that 12 to 17 has 54% of people owning an MP3 player, or 54% from that randomly selected group owning an MP3 player. So your problem is to make a well-labeled bar graph to display the data and describe what you see. All right, so for A, yep, not going to work. For A, you have to have a y-axis. Whoa. No. A y-axis and an x-axis. That line could be straighter, but we're going to deal with it. Over on the left side, you're going to label it as percent owning MP3 player. And across the bottom, you're going to label it as age group, and that is in years. All right, so whenever you are coming up with your scale for your y-axis, which in this case is going to be the percent of people owning an MP3 player, you want to use a scale that makes sense. And so if you look, we've got 5, 13, 30, 30, and 54. So it might be useful to do a 10-point scale because we kind of go from way down here at 5 all the way to 54. So I'm going to use a 10-point scale and say, okay, this is 10, this is 20, there's 30, 40, 50. And then I'll extend it a little bit and put 60 up here. All right, then I'm going to draw a bar for each one of these age groups. So I'm going to do 12 to 17 first, and 12 to 17 goes to 54%. So it's up here past 50, but a little bit less than halfway between 50 and 60. So there's my bar for 12 to 17. All right, 18 to 24 is at 30%. So I'm going to make a little space, go to 30%, do my bar, and this is 18 to 24. 25 to 34 is also at 30%, so I'm going to go to about the same place and do 25 to 34. 35 to 54 is at 13%, so not quite between, halfway between 10 and 20, so a little bit less than that. Let's say somewhere right in here. And this is 35 to 54, and then 55 and older is down at 5%, so halfway between 0 and 10 over here at 5%, and that's 55 plus. All right, B asks you, would it be appropriate to make a pie chart for these data, and why or why not? And so making a pie chart to display these data is not appropriate because each percent in the table refers to a different age group, not to parts of a single whole. So if you think about it, whenever we talk about 54% owning an MP3 player in the 12 to 17 group, that means that 54% of the people that were surveyed that fell into this range owned an iPod, and so, or an MP3 player. And so we're not talking about 54% of the whole. Another way you could think about that is a whole should be 100%. But if I add up 54, 30, 30, 13, and 5, I'm going to be well over 100%. And so this is not going to give us the entire piece of the information that we need, but each one of these categories represents 54% of the people that were 12 to 17 owned an iPod. 30% of the people that were surveyed that were 18 to 24 owned an iPod. So, of course, we have graphs that are good and we have graphs that are bad. Bar graphs compare several quantities by comparing the heights of the bars that represent the quantities. Our eyes, however, react to the area of the bars as well as to their height. When all the bars have the same width, the area, width times height, varies in proportion to the height, and our eyes receive the right impression. When you draw a bar graph, make the bars equally wide. Artistically speaking, bar graphs are a bit dull. It is tempting to place the bars with pictures for greater eye appeal. Don't do it. The following example shows why. All right, so in this picture, it kind of gives us an idea of who buys iMacs. And so when Apple Incorporated introduced the iMac, the company wanted to know whether the new computer was expanding Apple's market share. Was the iMac mainly being bought by previous Macintosh owners, or was it being purchased by first-time computer buyers and by previous PC users who were switching over? To find out, Apple hired a firm to conduct a survey of 500 iMac customers. Each customer is categorized as a new computer purchaser, a previous PC owner, or a previous Macintosh owner. The table summarizes the survey results. So you can see in our table that we have the different groups. Previous ownership, this would be totally new computer owners. These would be PC owners that switched over, and these would be repeat Macintosh owners. And so you can see the count as 85, 60, 355, and then the total being 500. So what this means is, of the 500, 355 were repeat Macintosh buyers, 60 were people that switched over, and 85 were people who had never purchased a Macintosh or a PC or a computer of any kind, and so there were 85 of those people. And so then it gives you the percent over to the side that corresponds with those. So 71% of the 100% total were repeat Macintosh owners, 12% were PC switchovers, and 17% were totally new computer owners. The problem is, in the graph that's over to the left, the graph of the data that uses pictures instead of the traditional bars, how is this graph misleading? And so it shows that you have Macintosh owners have the hugest computer. They also have the biggest amount, the highest total. Windows owners, though, or PC owners, there were 60 of them, and they accounted for 12%. But looking at how this looks, it makes it look like they were like hardly anything. And then it shows people that were new computer owners at none. This computer is quite a bit bigger than this. But if you look at your actual counts, the people that were new computer owners were only at 85, and the PC owners were at 60. And so that looks like quite a big difference here. Also, if you think about it, is this 85 is almost 100. Is this computer 3.5 times as big as this one? I would say no. So, although the heights of the pictures are accurate, our eyes respond to the area of the pictures. The pictograph makes it seem like the percent of iMac buyers who were formerly Mac owners is at least 10 times higher than either of the two other categories, which isn't the case. B says, two possible bar graphs of the data are shown on the next page. Which one would be considered deceptive and why? So if you're looking at this, what is deceptive is the bar graph on the right is super misleading. And by starting the vertical scale at 10 instead of 0, so as you can see on the y-axis here, we start at 10 as opposed to where we started at 0 over here. It looks like the percent of iMac buyers who previously owned a PC is less than half the percent who were first-time computer buyers. We get a distorted impression of the relative percents in the three categories by starting our y-axis off at 10 as opposed to starting it off at 0. Two-way tables and marginal distributions. We have learned some techniques for analyzing the distribution of single categorical variable. But what do we do when a data set includes or involves two categorical variables? We begin by examining the counts or percents in various categories for one of the variables. Here's an example to show what we mean. So this example gives the relationship between two categorical variables. A survey of 4,826 randomly selected young adults aged 19 to 25 asked, what do you think are the chances that you will have much more than a middle-class income at age 30? The table below shows the responses, omitting a few people who refused to respond or who said they were already rich. And so your table is titled Young Adults by Gender and Chance of Getting Rich. And so you can see that you have your opinions over here. So almost no chance, some chance but probably not, 50-50 chance, a good chance, almost certain. And then you have your totals down at the bottom. You have your genders, you have your females and your males. So you can see that you had a total of 2,367 females and 2,450 males for a total of 4,826. You have your total over here so that you can see the total of people that said almost no chance was 194. 96 of those were females, 98 of those were males, and you can kind of get the rest of your information from that just by looking at the numbers in your chart. So a two-way table is a table that displays two categorical variables in comparison to one another. And so if we backtrack a minute and we go back to our table, the two categorical variables that we were talking about in this particular two-way table are gender, male and female, and your opinion of whether or not you're going to get rich. Marginal distribution is the distribution of values of a variable in a two-way table among all individuals described by the table. So the way that you can find out the marginal distribution is by dividing each row total by the table total and converting to a percent. So if you were looking like at the almost certain, what you would do is you would say, I have 1,083 people who are almost certain that they're going to get rich, and I divide that by the total of people, which is 4,826. When I do that, I get 0.224, and as a percent, that is roughly 22.4%. Alright, so this is the same table again, and the problem this time is to use the data in the two-way table to calculate the marginal distribution in percents of the opinions. So remember to do the marginal distribution. What you have to do is you have to say that you are going to take the total. So if you're doing almost no chance, you would take 194 and you would divide it by 4,826, and that would give you 0.04, which is roughly 4%. So you have 4% of people saying they have almost no chance of being rich by the age of 30. Some chance you do the same thing, so the total is 712 out of 4,826. And that would give you roughly 0.148, which gives you 14.8%. And I'm not going to go through and do them all, but you do them all exactly the same way. Just to give you an idea about the rest of them, 50-50 chance would be 29.3%. A good chance would be 29.4%. Almost certain we talked about is 22.4%. So now we kind of have a percent for each one of them. Alright, so now that we have a percent for each one of them, we're going to make a bar graph that gives us a visual display of the marginal distributions. And so you're going to label your y-axis as your percent, and your x-axis is going to be your survey response. All right, so a good scale, if you're looking at it, you had 4%, 14.8%, 29.3%, 29.4%, 22.4%. So a good scale would be probably to go by 5. So we're going to start at 0. We've got 5. There's 10, 15, 20, 25. Oh, no, and 30. All right, so if we start out with almost no chance. We had 4% that said almost no chance, so not quite to 5. It's going to be difficult to label this, but almost no chance. All right, then we had 14.8%, so almost to 15, but not quite there. And this was some chance, but probably not. 29.3, which was almost to 30. Was our 50-50 shot. 29.4 was a good chance, so just a little, tiny little bit higher than the one we just did. But still not quite at 30. That one's a little sad. This is a good chance. And then almost certain, 22.4. So a little bit above 20, not quite 25. So some definitions. You have conditional distribution. Conditional distribution describes the values of a variable among individuals who have a specific value of another variable. So your conditional distribution of opinion among women, you had almost no chance. If you look back at your original table, your almost no chance, there were 96 women who said almost no chance out of a total of 2,367 women. So I'm going to flip back to that table real fast so you can see that. So you have your females that said almost no chance out of your total females. This is not over your total, because you are looking at the values of variables, of individuals with a specific value of another variable. So some chance you had 426 women out of 2,367 for a total of 18%, and so on and so forth. To do male, you had almost no chance, and the number of almost no chance for males was 98 out of a total of 2,459. So 98 out of 2,459 would be 0.039, which would be 0.04, which would be 4%. For your sum chance you had 286 out of the total 2,459. So if you did 286 out of 2,459, you would get 0.116, and so that would be 11.6%. And you could continue to do this for your males. A segmented bar chart. So a segmented bar chart is a chart which displays data about 2 or more categories in one bar, adding up to a total count or percentage. And so as you can see here on the bottom of our bar graph, we have our opinions. On the side, we have percent of gender in the opinion group. And so, of course, your almost nones, your total percent should be 100. Your sum chance 100, 50-50, 100. They should all be 100% because it should be the makeup of males and females that give you that. And so what they did was they found out how many females, they found out how many males, and they found that out of the percent of people that were almost none. And so when they did that, it was about split for almost none. You had about 50% female, 50% male. And for some chance, you had about 60% female said that there was some chance. Male said that there was about 40%. 50-50, again, is right there in the middle. So is a good chance, and almost certain is a little bit less than half for the females. So the males would be, I'd say 60, a little bit more than 60. All right, how to organize a statistical problem. You have a 4-step process. So the first part is to state what's the question you're trying to answer. The plan is how will you go about answering the question? What statistical techniques does this problem call for? Do, make a graph, and carry out needed calculations. Conclude, give your practical conclusion in the setting of the real-world problem. So on this example, you have men's and women's opinion. Based on the survey data, we can conclude that young men and women differ in their opinions about the likelihood of future wealth. Give appropriate evidence to support your answer and follow the 4-step process. So your first step is to state, and so you're going to state your question. When you state your question is, what is the relationship between gender and responses to the question? What do you think your chances are of getting rich they actually use having more than a middle class income, but we'll say getting rich at age 30. So then you have to state your plan. And so for your plan, it's kind of by looking at the information that we have, we might suspect that gender might influence a young adult's opinion about the chance of getting rich. So you might compare the conditional distributions of responses for men alone and then for women alone. All right, do. And so to do this problem, you're going to make a side-by-side. Bar graph to compare the opinions of males and females. And the last thing is to conclude. So when you conclude, you might say something like, based on the sample data, men seem somewhat more optimistic about their future income than women. Men were less likely to say that they have some chance, but probably not, than women. So their percentage of saying that was 11.6% versus women 18%. Men were more likely to say that they have a good chance at 30.8% versus a women's 28%, or are almost certain 24.3% for men versus 20.5% for women to have much more than a middle class income by age 30 than women were. So it appears, if we were going to say this again, we might say men have a somewhat more optimistic outlook on getting rich than women. All right, next definition that we're going to talk about is association. So there is an association between two variables if specific values of one variable tend to occur in common with specific values of another. So an example of that would be like in our previous information, both graphs provide evidence of an association between gender and opinion about future wealth in this sample of young adults. That is, the variables of one variable, or the values of one variable, which is the opinion, tend to occur more or less frequently in combination with specific values of the other variable, gender. Men are more often rated their chances of becoming rich in the two highest categories. Women said some chance, but probably not much more frequently. How can we say that there is an association between gender and opinion in the population of young adults? Making this determination requires formal inference, which we will have to wait for chapters for. But we can say that there seems to be some sort of relationship between gender and their feeling about becoming more wealthy than middle class by age 30. All right, the next thing we're going to talk about is Simpson's paradox. Simpson's paradox is an association between two variables that holds for each variable value of a third variable can be changed or even reversed when the data for all values of the third variable are combined. So that sounds like a really big mess. And so to kind of give you an idea of what that is talking about, there's this example that has to do with medical helicopters and how they save lives. And so basically the gist of it is half of the helicopter transport patients are from serious accidents compared with only 100 of the 1,100 road transport patients that this particular example is talking about. So the helicopter carries patients who are more likely to die. The seriousness of the accident was a lurking variable that, until we uncovered it, hid the true relationship between survival and the mode of transport to the hospital. So I imagine that we will spend a lot of time talking about Simpson's paradox. So don't feel discouraged if you are not quite sure what it's talking about today. We will cover this more in class, more in depth.